As you may have gathered by now, though, that I believe in six-day creation as written in the Genesis record, and that the creation of this universe, including the stars and galaxies, was on day 4 of creation week, about 6,000 or 7,000 years ago. But I also believe God has given us the ability and inquisitiveness and desire to understand the nature of his creation, in particular the universe. I think the structure of the universe is it's all part of God's creation, and it all came into existence by him and is preserved by him. Possibly one of the biggest, I would say probably the biggest question that we really have to answer if we take this position is to explain starlight in this enormous universe. And I'm not going to talk about the size of the universe, but I find no problem with the distance scales in the universe that we see galaxies, for example, in the Hubble Deep Field, 6 or 7 billion light years away. And on the surface, that sounds like it should take light 6 or 7 billion years to get to Earth from those galaxies, assuming constant speed of light and so on. So that's really what I want to talk to you tonight. And as I must warn you though, in this talk, there is definitely some physics. There will be some equations. Gasp! No, not equations. There'll even be some graphs. Ooh, I can see the cheap seats are moaning already. But don't worry, I hope I can explain it to you as we go. Have you seen this sort of thing in the media? We hear about this stuff called dark energy and dark matter. It is believed that the universe is made up largely of this stuff. 95% or so of the stuff of the universe is dark energy and dark matter. That other little segment there called baryonic matter, 4%, that's the stuff you're sitting on. Those chairs, this room, this planet, you, electrons, protons, neutrons, that sort of stuff. If you recall, on Monday night, I was talking about testing the Friedmann-Lemaitre model of the standard Big Bang model. They have to invoke dark energy and dark matter for the theory to fit the observations. For example, those high redshift supernova measurements. And I want to show you a bit more tonight about how some of that has come about. But if I could show you another theory that fits the same data, same observations, without dark matter or dark energy, then that would discredit the Big Bang, wouldn't it? Okay. Let me take you back to high school. I hope you can remember. How do you measure the mass of the sun? Very simple, really. All you need is Newton's law of motion, gravitation. And you get this equation there, m equals v squared r over big G, G the Newtonian gravitational constant. So all you need to know is the velocity of a test particle around the sun and the distance that test particle may be. This is a sun here in all its glory that gives life upon our planet. To measure the mass of the sun, all we need to do is look at the speed of the planets, or particular planet, rotating around that central massive body. We measure the speed, the rotation speed, and the distance, and then plug it into that formula. And this is quite easy. If we move out further and further, we can pick any planet we like, and we'll get the mass of all the planets included inside that orbit, the sun plus all the other planets. And we can very accurately measure the mass of the sun, and hence by doing this process, even the masses of the included planets as we go out. This mass measurement is then called dynamical mass. Can you remember that? So it's measured dynamically. Okay, when astronomers in the late 1800s, early 1900s looked at the planet Mercury, which you should now be seeing, we see the planet Mercury going around the Sun. Now everyone knows that's the innermost planet. You'll notice something strange about its orbit. Even though its orbit is slightly elliptical, and as it comes back around, you see it doesn't perfectly retrace on its orbit. This was a real problem to astronomers because they noticed that orbit over time, over a century in fact, could not be properly accounted for by the laws of physics as we knew, which was Newtonian physics. There was a very tiny progression, or we call advance, of the perihelia, the point of the end of the ellipse, if you like, would rotate around like a rosetta. And this couldn't not be accounted for even when we allowed for the mass of the other planets like Venus and Earth and so on. This was a tiny 43 seconds of arc per century. That's absolutely minuscule, but astronomy was very good in the late 1800s, and it really troubled astronomers. So guess what they did? To solve the problem, they invoked what? Dark matter. You guys have read my book already. Some suggested that there was an inner asteroid belt between the Sun and the planet Mercury. Now, it was dark matter because this asteroid belt could not be observed. Can't see something, hence dark matter. Dark matter solved the problem. Some also suggested, no, there was another planet, the planet Vulcan, that lived behind the Sun. You know, that's why the planet Vulcan was so hot. If you look it up on the internet, you find Spock had copper-based blood. Very hot planet. The idea of the planet was it was so close behind the Sun, as the planet Earth moved around, Vulcan perfectly matched the orbit of the Earth and it could never be seen, therefore it was dark matter. Dark matter come to the aid of the astronomer and solve the problem. If you look that up on the internet, actually, you'll find that the planet Vulcan is 16 light years from our solar system, therefore it can't possibly have been the planet Vulcan. Right? No. That's fiction, guys. Come on. See, the problem was this. They were trying to invoke unseen matter when the solution of the problem was it needed new physics. Einstein in 1916 published his general theory of relativity. That general theory of relativity introduced the concept of space-time curvature, which I'm going to tell you a bit more about tonight. But that added an extra component in the force equations that provided a small additional amount, that very 43 seconds of arc per century, that solved all the problems. So new physics came to the rescue. Well, it doesn't stop there. It doesn't stop in the solar system. If you go out further, and let's have a look, for example, at a spiral galaxy. Now, we're looking edge-on this spiral galaxy, and if we could plot the speeds of rotations of the stars in the spiral galaxy as we go out from the centre, here I have it along that graph plotted in light years. So if you move out from the centre of the galaxy, and we can measure the speed of the stars in the galaxy from the Doppler effect. Because the gases emit light and we receive the light from the galaxy, and when the light is coming from gases that are moving toward us, it is blue shifted. Everyone say blue shifted? Blue shifted. If the gases are moving away from us, it's gray shifted. You guys are brilliant. You'll get a university degree in this in no time at all. In fact, if you look at my graph here, you see if you move out far enough in the disk of the galaxy, you don't even need stars. You just use the gases that are emitting this radiation, and we can use the same equation that we used in the solar system to measure the mass of the included mass of the galaxy. You see what we're doing? Exactly the same thing. But there's a problem, and the problem you may already notice is that as you go further and further out from the central galactic bulge of the galaxy, the speeds of those rotating gases and stars never go slower and slower. In the solar system, the further you go away from the sun, the slower and slower the rotation, the years are for the planets to get around the sun, which is what we expect from Newtonian physics. Doesn't happen. In fact, there are hundreds of thousands of spiral galaxies where this has been measured, and it doesn't happen. And the problem, it's an enormous problem. So guess what the astronomers did? Yes, very good. They invoked dark matter. They said these galaxies must be shrouded in a spherical halo of invisible dark matter. In fact, up to 80 or 90% of the whole galaxy must be made of dark, invisible matter. You see the central bulge of the galaxy that has most of the luminous matter, and then there's a thin disk, which, by the way, in our galaxy, we're way out in the thin disk region. And then most of the matter surrounding the galaxy would be this dark stuff that solves this problem. And they measured the mass of galaxies this way, from the same calculation that I showed you earlier, but they have to invoke the dark matter because they're from the dynamical mass, measured from that rotation speed of those test particles, there's too much matter. What they observe is somewhere between 2 and 7 times less by just looking at the visible matter in the galaxy. And so most of what a galaxy is should comprise of dark matter. And then if we look at clusters, this is a cluster in the Abell group. There's hundreds or maybe even 1,000 or so galaxies in that cluster, and we can measure the speeds of the galaxies orbiting within the cluster. They orbit around their common centre of mass. And we can do the same thing, measure the dynamical mass of the cluster from the orbit speeds of those galaxies. It's actually more correctly from their dispersion, which is the differences between them. And we get also more mass, much more mass than we can observe. In fact, if we look in a plot here, which I've shown starting in small structures like galaxies at the top, and light years is a sort of the radius of the structure in the universe. And what I've written there, m over L, this mass to light ratio, means the mass calculated dynamically as compared to the mass from observation, from the luminosity coming from those structures. And you see, as you go from galaxies to clusters of galaxies, small clusters, binary groups, to large and larger clusters on very large scales, the amount of mass missing becomes absolutely enormous. In very large clusters, it's 99.99% of the cluster is dark matter. This is where they get this stuff from. But we should learn from history, shouldn't we? Some years ago, I had the opportunity to meet a theoretical physicist. At the time, he was the Einstein Professor of Theoretical Physics at Ben Gurion University. That's him there visiting me in Fremantle. We went for fish and chips down at Cicerello's in Fremantle, and we had a good discussion. It spent some time, and I started to collaborate with him. He, at one point, published a paper that I found very curious, and I'd like to point the title to you. He talked about a deviation from this Tully-Fisher law, and it said, doubts about the necessity and existence of halo dark matter. That's that halo I showed you around the galaxy. He had a new cosmology, a new idea. This is his book called Cosmological Special Relativity, this one. Talks about the large-scale structure of the universe, where he invoked a new idea in physics in cosmology. His cosmology was not 4-dimensional, but 5-dimensional. Ooh, here we go now. Moving out of what we thought we could have familiarity with. 4 dimensions is pretty tough enough, isn't it? 5. The new dimension is the expansion of the fabric of space itself. Space is not nothing. Vacuum is something. If you could pump all the matter out of vacuum, you'd still have something. There's still energy there. So the fabric of space could be viewed as something. Often in these textbooks you see it as like a rubber sheet, as that's an analogy of course, but it's something. And his theory the galaxies embedded in this material, this vacuum material, and the vacuum or the space itself is rapidly expanding in an expanding universe, of course. And he treats that as a new dimension. And it's quite legitimate to do so, just as much as time is a new dimension. It's not something you can measure with a ruler, you need a clock to measure it, and the velocity dimension in this new cosmology, you need redshift to measure it. So that's really interesting too. This is a slide here I stole from Wikipedia, which of course the slide originally was based around the classic Big Bang cosmology. But it illustrates a point because starting from this singularity and this new cosmology of Carmeles is a sort of an alternate Big Bang cosmology that I'm going to borrow and use for creationist purposes. It's legitimate to do that sort of stuff. Because if you think about it, just think about it for a moment, and hope I don't horrify you here, but the Big Bang model, in some sense, is pretty good. And what I mean by that is it begins in time. It has a point in creation. It's finite. Things like that. And you can understand why people back in the 1950s favoured such a notion, when the dominant cosmology at the time was the steady-state theory, the eternal universe that didn't begin in time, had no beginning and had no end. You can see that sort of atheistic concept there. And so to have a model that begins in time had some sort of consistency with the Bible, right? But of course it carries a lot of other baggage, and of course that I reject. But I can see in some ways that there is something we can use, and so if it's what's good, let's borrow it and let's use it. And note too that many of the cosmologists who are anti-Big Bang are that way because it's too close to the biblical idea of creation. I was recently at the second cosmology conference called Crisis in Cosmology, and I asked a number of the people there why they reject the Big Bang model. Ultimately, they came to the point where they said it's philosophical because they don't want to accept a God or a creator. So in the usual representation we have of general relativity, we're often shown this illustration of a massive object in the center, and we have like a planet or a test particle moving around it. Because of the curvature of space-time introduced by that mass, it causes that extra acceleration, and hence in the case of the planet Mercury, provided that extra component to cause the orbit to precess. And of course this happens also in other bodies, massive objects and so on. If we look at the theory we get from the new physics, and I'm not suggesting that you try to fully understand these things because I've just given you a couple of equations there, but the top equation is just standard Newtonian physics that you get in high school or first year university. That is still true in the new theory. So it's still the normal four-dimensional stuff is true, but it introduces a new equation, a new degree of freedom, and provides new physics that helps solve some of these problems. And you put them both together, and I call that Carmelian physics. If we look at galaxies, and if we look at them sort of stand back and look at a galaxy, it generally looks like it rotates as a whole. Now, I'm not saying it's solid body rotation, it's not. But remember, if we see the speeds of rotating stars in galaxies, they seem to, on the edges anyway, in the disk region, all move at the same tangential velocities. And from this, people have derived what's called the Tully-Fisher law. I mentioned it earlier in that paper title. It's the relationship between the rotation speed of a galaxy and its luminosity, or that's related to its mass. People have used this as a method actually of measuring distances to those galaxies. Well, if we think about a galaxy then, that Newtonian physics applies to particles moving around in space, around that central galactic core in space. The Carmelian idea is that space is expanding in every direction, of course, but if you think of it expanding around the circular direction of the galaxy, then space is kind of moving in some sense. And so particles are not constrained to be held there. Like in Newtonian physics, the particles are all constrained by the force of gravity. But in the Carmelian theory, because space can be moving also, they're free to circulate with the movement of space. And I'm trying to illustrate this to you with these little diagrams here. So in this case, we had the earlier illustration of the particle moving in a sort of a fixed space-time that's curved, right? That's the green dot. But the green dot is moving in space. That's the Newtonian idea. But when the space is also expanding, if you like, circularly around the centre of the galaxy, it's also being dragged around a bit by some extra component. And then if we look at another one where we consider a particle that's right out on the edge of the galaxy, where there's no Newtonian force left, no acceleration component that would push it around, it's like the only thing left that causes that red particle to move is the expansion of space itself. So the inner green one is like the normal Newtonian physics, and the outer red one is this new Carmelian term. Well, if we look at what the accelerations are like for a typical galaxy, we see that the red one out in the outer regions of the galaxy, this is out where my red arrow is there, you see the accelerations are very weak, and they drop off of 1 over the inverse distance. And everyone knows from high school physics that Newtonian force law drops off as 1 over r squared, right? So in the central part of the galaxy, it's Newtonian, normal Newtonian physics applies, but out further in the disk of the galaxy, where the strange stuff happens, it drops off as 1 over r. And we get, from this theory, we get the typical rotation equations, but in the Carmelian theory, we have the velocity of or the speed of the gases in the galaxy. The fourth power of it is proportional to the mass. Therefore, it should be constant. And if we actually, and I'll show you a graph of a real galaxy curve. This is the spiral galaxy 2903. And you see in near the central bulge of the galaxy, that's down near where the radial position is towards 0 there, that's written in kiloparsecs, that's just 3,000 light year units. You see it's Newtonian, follows Newtonian force law, but when you go out into the disk region of the galaxy, it follows the Carmelian law. It's no longer Newtonian. If it were truly Newtonian, the speeds of those stars and gases should fall off as the green curve. It should get weak, slower and slower and slower as you get away from the centre of the galaxy. So that's measured data fitting the theory, fitting pretty well, right? Any dark matter needed? None whatsoever. So did we need dark matter? No. But what we've got is new physics, a new degree of freedom introduced by new physics. And if we look at a bunch of galaxies, this is just a sample, we see the masses calculated, dynamical masses calculated using Newtonian physics, and I've just written the numbers there, and we compared them with the Carmelian physics, and the ratio is what's important. You see, using the ratio tells you how much missing mass there kind of is, missing in inverted commas, because it's not really there. We don't need it. So when you use the Carmelian physics, you don't need to invoke dark matter at all. The bottom one I've just illustrated because that's the Milky Way galaxy. Our solar system is spinning around a point in the galaxy at around 220 kilometres per second, which is far, far, far too fast for Newtonian physics. And so in the past, they've said our galaxy has about 4 times too much mass, unobserved mass. That's the missing dark matter. But with the new theory, all solved. No problem. We don't need any of that stuff. So no fudge factors. Now I know you're all wondering, where is he going with this? Trust me, hold on, I am going somewhere. I'm trying to establish to you that the theory works. The new theory has observational applicability. because that's the best we can do when we're dealing with the cosmos. Propose a model and test it by observations. Do you remember this? We talked about redshift. We talked about looking at the light from the distant galaxies, and we see that everywhere you look in the cosmos, the light is redshifted. Redshift, for those who weren't here, simply means we're looking at those spectral lines coming from the gases in the star or from the galaxy itself, and we notice that they're generally shifted towards the red end of the spectrum. That was interpreted in 1929 by Edwin Hubble, that meant that the galaxies were rushing away. In fact, they were rushing away in every direction of the sky that you look, no matter which direction. And he came to the conclusion from that fact that the greater the distance you looked, the greater the redshift of those galaxies on the surface, that he realized that kind of meant he must be standing at the center of the visible universe. And of course, that was totally abhorrent to him as an atheist, and he introduced alternative ideas invoking the space-time curvature principle, finite closed universe, and so on, to get around that problem. And I illustrated that to you by that surface of the balloon analogy. But the Hubble law seems to be fairly robust. Many galaxies have been measuring their luminosity and their redshifts, and it does seem to follow some kind of trend. And so the idea is, and remember this is in an inference, an interpretation, people then use the Hubble law to calculate distances in the universe. In fact, that's the main principle used, and they use that to then test the Friedmann-Lemaitre models, the standard Big Bang models, against observation. And that's how it's been tested, and using those tests, which I showed you in the last talk, and these galaxy rotation curves, they've invoked those type of percentages of dark matter and dark energy in the universe. Well, the new theory envelops, if you like, all of general relativity. All of the tests that we have successfully done on general relativity in the solar system are also true in the new physics, which only has this one extra degree of freedom after all. The new theory was originally formulated by Moshe Carmeli on his kitchen table in the middle of the 1990s in Israel, and in 1996 he predicted not only should the universe be expanding, but it should also be accelerating. That was a prediction, clean prediction of his theory. In 1998, two independent teams of astronomers measuring high redshift supernova, those exploding stars, the Type 1a supernova, they both independently established that the very distant ones were much dimmer than they ought to be, and therefore they said the universe is not only expanding, but it must also be accelerating. But note, I will add a caveat there, that's an interpretation, assuming that no other mechanism could be found for their observations. Again, remember, this is an inference. Okay, but not a bad prediction by Carmeli, nevertheless. His model has certain basic assumptions, but they're few. The standard Big Bang model has many, and many ad hoc, add-on patches, patch after patch after patch. His were basic. He needed a spherically symmetric, isotropic expanding universe. He didn't need homogeneity. Do you remember that about the homogeneous universe? I showed you the universe is not homogeneous. And that actually must mean that the Friedmann-Lemaitre standard Big Bang model is wrong in itself. He didn't need that, just a spherically symmetric one. And he invoked the Hubble law as fundamental, that it was like his fundamental primary axiom that the universe is expanding in every direction. The galaxies are stationary in the space, and they're being dragged along for the ride, so to speak. He had only a few observables, very, very few. Distance, redshift, and the density of matter in the universe, which was unknown. Standard Big Bang model has many, many parameters that have to be fitted. I think in the latest consensus cosmology, the number is up to around about 18 free parameters. His was much simpler. I found that very appealing because it was so simple and maybe had some truth in it. Just reiterating what they claim, because of these type of calculations, they have this 22% dark matter and 74% dark energy, the dark energy being the driver of the accelerating universe. It's sort of a negative pressure. That's something that doesn't exist in the lab, never been observed. Remember, I told you cosmology is all about describing unknowns with unknowns. They have an accelerating universe driven by dark energy, and of course there's a big component of dark matter as well. What we normally understand as proofs in physics is about our ability to test, to repeat and to run experiments. In the cosmos, outside our solar system, we are totally subject to observation only, and there is really no way we can interact with the universe, so it becomes much weaker. And I showed you from the Carmeli theory, we only need this 4% baryonic matter. We don't need any of the other stuff. Problems solved, no fudge factors are needed, you see, with the new theory. I showed you this plot, I showed you the structure of the universe, that it fits within the new theory, a spherically symmetric theory. Also, the theory can describe a finite, bounded universe, a universe that I believe the Bible suggests. I'm not saying I can prove it from the Bible, but I believe there are a finite number of stars in the universe. The new theory admits that solution. It also admits the other possibilities as well. You cannot tell from the data, from the observations, which is the correct one, but if you start with the Bible, it's consistent with this new theory. I love this, isn't there? There's always something good that comes out of this. We can always learn something more. And what we can learn is a solution to this problem, the starlight travel time problem. And we observe supernova. We observe exploding stars. And I've illustrated the one here, the 1987 one. This is supernova 1987A. That's when the astronomers first saw it, so that's what it's named. It was in the Large Magellanic Cloud, which is about 170,000 light years away. So on the surface, that should mean the light should take 170,000 years to get to Earth. How do we see it if the universe is only 6,000 or 7,000 years old? Also, we observe supernova in nearby galaxies, like in the Andromeda Galaxy, 2.5 million light years away. How can we see that if the universe is so young? You see the problem? Let's imagine, though, I'm a clockmaker, if you like. I build high-precision oscillators and clocks. So I want you to now start thinking of astronomical clocks and Earth-based clocks. Clocks are this instrument we use to measure time. And I want to take you back a little bit, and I'm just going to use Venn diagrams for this, but I want to tell you that special relativity, Einstein's theory, has been thoroughly tested in our solar system, many, many times over. A theory is tested by repeatable experiment, and it's quite robust. The new theory, cosmological special relativity, obviously has not been tested in the solar system, but it seems to apply on the large-scale structure of the universe. Now, if we can imagine for a minute we have an expanding universe without any matter in it. I know this is a little hard to imagine, but we can just work with the mathematics at that level and everything seems to work fine. So we can put that together as a three-dimensional theory that on the small scale in the solar system, we have Einstein's special relativity. On the large scale in the cosmos, the expanding universe, it describes the expansion of the universe very nicely, and it works on that scale. But is there any special frame of reference? Do we live in a preferred place in the universe? Let's put the matter in now. If we put matter back in, then we are forcing a special condition on the universe if we remember what we observe, that it looks like we are at the centre of a large sphere of concentric shells of galaxies, and our galaxy is somewhere near the centre of it. We then look at general relativity in our solar system, tested extremely well, verified many, many times over. We look at the new general cosmological general relativity, and we fit it to things like the high redshift supernova measurements. Fits beautifully without any dark matter or dark energy. So we can describe all that without any of those fudge factors. Put those two theories together with a whole five-dimensional theory, and something we are forced to conclude something else. And what we are forced to conclude gives us a solution to the light travel time problem. So I'll reiterate that point. What I'm saying, if the one theory, the Einstein's general relativity theory, which we know works in the solar system, if that is true on the local scale, that's space and time, and if space and velocity, or space and redshift, from Carmeli's cosmological general relativity theory works in the large-scale cosmos, galaxies and the cosmos as a whole, clusters and so on. We have two successful theories on two different scales. If we put the two together, we are forced to conclude one point. And the one point works like this. At some point in the past, the universe was rapidly expanded. Rapidly expanded, I mean it was accelerated. The fabric of space was rapidly accelerated. Now, I can't tell you when that happened, but if I read the Bible, day 4 of Creation Week seems like the perfect opportunity for this to happen. God invoked a massive acceleration episode. During that process, and I told you this last time, particle production must occur. You get the formation of stars and galaxies during this rapid stretching process. Right? But because we have a spherically symmetric universe, the Earth is at the center in a special place, a special frame, if you like. And the clocks in the universe are all around the Earth. They tick at different rates, a faster rate than the clocks on Earth. That means the clocks on Earth during this rapid stretching phase of the 24 hours of Earth time tick about 1 trillion times slower than they do in the rest of the cosmos. You got that? I know that you should see the equations. So here's an illustration. This is meant to illustrate how this works. You see, during that day 4 of Creation Week process, we have the cosmos, clocks in the cosmos, flying around so fast, it's just a blur compared to the Earth clocks. And then suddenly, at some point, God stops that acceleration phase and all clocks in the cosmos tick at the same rate. From the theory, and I don't have time to go into it now, we only expect to see redshifts in the universe, but we expect billions of years of cosmic time to pass in the cosmos as compared to clocks on Earth. In fact, we must conclude from this that all light in the universe gets to Earth within 24 hours before Adam opens his eyes. When I was first working on this, I was talking to Carl Whelan about this, and I was saying, oh, look, it's within a day or even a year. But a close examination made me realize the light had to get there during this accelerating phase. It has to be within 24 hours. And what we see in the universe is perfectly matched by the theory that I've just told you works on all these other scales. And I've published nearly 10 papers in secular peer-reviewed physics journals describing Carmelian theory fitting the observations in the solar system, in the cosmos, galaxy rotation curves, clusters, and the large-scale structure of the universe. But we are forced to conclude this one point, that we have to have a massive time dilation event like this described in this animation. So if you missed what I just said, then make sure you get a copy of Starlight Time and the New Physics. Thanks so much.
Is the creation-evolution debate just a side issue? Can beliefs about where we came from impact the way people behave? How can we more effectively lead people to Christ when many believe science disproves the Bible? Some scientists say the world is billions of years old. Are they correct and the Bible wrong?
As a trained scientist, being a Christian, I had to try and juggle the millions of years of evolution with the Bible. And initially I was able to do that. But then I went along to a seminar, a creation seminar. I actually went along to tell these guys with PhDs where they were wrong. But during their presentation, I realised that I was the one who was wrong. You cannot fit evolution into the Bible, and you don't need to. The sorts of questions that I'm asked again and again: where did the races come from? Where did Cain get his wife? What about the dinosaurs? Are the sorts of questions that I used to challenge my Christian friends with when I was an atheist, and when they couldn't answer, I had no further reason to explore Christianity.
Dinosaurs was the biggest stumbling block for me because it was something, as a young child, I had been to museums, I had seen dinosaurs, I knew that the bones were real, I knew these were animals that had lived. But when I'd asked my RE teachers and Christians that I knew, and I pestered my RE teacher quite a bit about this issue, where are the dinosaurs in the Bible? And she did not know where she could find that, so rather than deal with my question, she put me out of the class eventually, and I just filled that time pursuing other interests. What changed my view was when I attended a creation meeting as a new Christian, and the speaker there was talking about all of the things that I'd had issues with, but especially dinosaurs and fossils, and how you can interpret that information with a biblical worldview, and I just found that really exciting as a new believer. The presentations are very easy to understand. Everything's done in layman's terms. There's a lot of PowerPoint presentation used as well. So very easy to understand, usually sitting on the edge of your seat through the whole presentation.
Questions about creation and evolution are a huge stumbling block for many, preventing them from believing the Bible. Creation evangelism is one of the most relevant and powerful methods of reaching our culture today. Find out how to use this fascinating information to reach your friends and neighbours. There's lots of free information on our website, creation.com.